Machine learning models do not improve simply because we train them longer or make them bigger. They improve because we measure them correctly and optimize toward the right objectives. Evaluation metrics are not just reporting tools, they shape how we interpret model behavior, how we compare systems, and ultimately how we design training pipelines. Among the most widely used metrics across AI systems are accuracy, precision, recall, F1 score, and, in the specific context of language modeling, perplexity. Each captures a different aspect of performance, and each has failure modes that technical practitioners must understand deeply. Start with accuracy, because it is the most intuitive and the most frequently misused. Accuracy is simply the fraction of predictions that the model gets exactly right. If you have 1,000 predictions and 900 are correct, accuracy is 90%. This seems straightforward, and in balanced classification problems it often provides a reasonable first glance at performance. However, accuracy assumes that all errors are equally important and that class distribution is reasonably balanced. In many real-world systems, neither assumption holds. Consider a fraud detection system where only 1% of transactions are fraudulent. A model that always predicts not fraud will achieve 99% accuracy while being completely useless. The metric is numerically high but operationally misleading. This is where precision and recall enter the picture. These metrics were designed to give more nuanced visibility into classification behavior, especially in imbalanced datasets and high-stakes detection tasks. Precision answers the question, when the model predicts the positive class, how often is it correct? It is the number of true positives divided by all predicted positives. Precision focuses on the reliability of positive predictions. High precision means that when the model raises an alarm, it is usually right. Recall answers a different question. Of all the actual positive cases, how many did the model successfully identify? It is the number of true positives divided by all actual positives. Recall focuses on coverage. High recall means the model is good at finding most of the relevant cases. These two metrics often trade off against each other. If you make a classifier very conservative about predicting the positive class, precision will usually increase because false positives decrease, but recall will fall because many true positives are missed. If you make the classifier very aggressive, recall increases but precision often drops. This trade-off is not a bug, it reflects real operational choices. In medical screening, high recall may be critical because missing a disease case is very costly. In spam filtering, high precision may be more important because false positives annoy users. The correct balance depends on the domain, not on abstract metric maximization. To understand this trade-off more concretely, it helps to think in terms of the confusion matrix. For binary classification, every prediction falls into one of four buckets: true positive, true negative, or false negative. Accuracy aggregates all of them into one number. Precision isolates the quality of predicted positives. Recall isolates the completeness of detecting real positives. Because precision and recall capture different aspects of performance, practitioners often want a single summary metric that balances them. This leads to the F1 score, which is the harmonic mean of precision and recall. The harmonic mean penalizes extreme imbalance more strongly than the arithmetic mean. If either precision or recall is very low, the F1 score will also be low. The F1 score is particularly useful when the positive class is rare and both false positives and false negatives matter. However, it still encodes a specific assumption, that precision and recall are equally important. In some applications this is not true. Variants like F-beta scores allow weighting recall more heavily than precision or vice versa. An important technical subtlety is threshold dependence. Many classifiers output probabilities or scores rather than hard labels. To compute accuracy, precision, recall, or F1, you must choose a decision threshold. Changing the threshold changes all these metrics. A model does not have a single precision or recall, it has a precision recall curve across thresholds. This is why experienced practitioners examine curves rather than single-point metrics during model evaluation. Precision recall curves and ROC curves reveal the trait space and allow selection of an operating point appropriate for the application. Now let's shift to language models. where evaluation has a somewhat different flavor. Language modeling is typically framed as a probabilistic next token prediction task. Instead of discrete class labels, the model outputs a probability distribution over a very large vocabulary. Traditional classification metrics are not well suited to this setting. Instead, the dominant metric is perplexity. Perplexity is fundamentally a measure of how well a probability model predicts a sequence. Formally, it is the exponential of the average negative log likelihood per token. Intuitively, perplexity measures how surprised the model is by the actual data. Lower perplexity means the model assigns higher probability to the observed text, which indicates better predictive performance. A useful mental model is that perplexity roughly corresponds to the effective branching factor of the model's uncertainty. If a model has perplexity of 10, it is, on average, as uncertain as if it had to choose uniformly among 10 options at each step. If perplexity drops to 5, the model's predictions are much sharper. Perplexity has strong theoretical grounding in information theory. It is directly related to cross-entropy and to the concept of entropy in probability distributions. Because language modeling training typically minimizes cross-entropy loss, perplexity is a natural evaluation metric. However, perplexity also has important limitations that advanced practitioners must keep in mind. First, perplexity is tokenization dependent. Changing the tokenizer changes the numerical value of perplexity, sometimes dramatically. This makes cross-model comparisons tricky unless tokenization schemes are aligned. Second, perplexity measures next token prediction quality, not downstream task usefulness. A model with slightly better perplexity may not produce noticeably better generated text for users. This disconnect becomes more pronounced in large generative models where human preference and factual accuracy matter more than raw likelihood. Third, perplexity averages over the entire distribution. It does not directly capture rare but important failure modes such as hallucinations, toxic outputs, or reasoning errors. This is why modern evaluation of large language models increasingly includes task-based benchmarks and human evaluation alongside perplexity. Another subtle issue is exposure bias. Language models are trained to predict the next token given ground truth previous tokens, but during generation they condition on their own outputs. Perplexity does not capture this mismatch. A model may have excellent perplexity yet degrade during long-form generation because errors compound. For technical audiences, it is also useful to connect perplexity back to cross-entropy loss. If the average cross-entropy per token is h, perplexity is simply the exponential of h. This means improvements in cross-entropy translate exponentially into perplexity improvements. Small changes in loss can produce noticeable perplexity shifts. In large-scale training, perplexity curves over time are one of the primary diagnostics for training health. Smooth monotonic decline typically indicates stable learning. Plateaus, spikes, or divergence often signal optimization issues, data problems, or numerical instability. It is also important to understand that perplexity varies significantly across domains. A model trained primarily on news text may show low perplexity on similar text but much higher perplexity on code, poetry, or specialized technical material. Perplexity is always relative to the evaluation distribution. Returning briefly to classification metrics, there is growing interest in calibration. A model can have high accuracy but poorly calibrated probabilities. Calibration measures whether predicted probabilities correspond to true empirical frequencies. In many decision systems, especially risk-sensitive ones, calibration is as important as raw accuracy. For imbalanced problems, practitioners often examine precision recall AUC rather than ROC AUC because it better reflects performance on the minority class. The choice of evaluation metric should always reflect the operational objective, not just convention. In multi-class settings, averaging schemes introduce further nuance. Metrics can be macro-averaged, micro-averaged, or weighted. Each answers a slightly different question about model performance. Macro-averaging treats all classes equally. Micro-averaging weights by sample count. Weighted averaging balances by class frequency. Choosing the wrong averaging scheme can lead to misleading conclusions. In large language model evaluation, there is an increasing recognition that no single metric captures quality adequately. Perplexity measures probabilistic fit. Accuracy-like metrics apply to specific benchmarks such as question answering. Human evaluation captures fluency and usefulness. Safety metrics capture harmful behavior. Modern evaluation pipelines combine many signals. The deeper lesson across all these metrics is that evaluation is a modeling choice. Metrics encode value judgments about what errors matter. They shape optimization targets and influence model design. Treating metrics as neutral numbers is a common but costly mistake. An experienced practitioner constantly asks, what behavior does this metric reward, and what behavior does it ignore? For example, optimizing purely for accuracy in imbalanced detection systems often leads to degenerate models. Optimizing purely for perplexity can encourage overly generic language generation. Optimizing purely for F1 may hide calibration problems. As AI systems become more integrated into real-world decision loops, metric selection becomes even more consequential. Metrics guide not only research comparisons but also deployment decisions, monitoring alerts, and retraining triggers. The most important mental model to retain is that each metric provides a different projection of model behavior onto a single number. Accuracy measures overall correctness under equal weighting. Precision measures trustworthiness of positive predictions. Recall measures coverage of true positives. F1 balances the two. Perplexity measures probabilistic predictive quality in sequence models. None of these metrics is universally sufficient. Each is a lens, and responsible system design requires looking through multiple lenses before drawing conclusions about model quality.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.